I'm sure it's but you yeah, it's okay. I should. I kept doing yeah, I did actually after each. Oh no. Yeah, I love his water. Something from Rockets. Yeah, I was oh, yeah. That's awesome. Oh yeah. No, that's not what I was trying Did you post on the whole time? I think it was G Loss. He's not here yet. But I was curious. You there? Yeah. You did? Yeah, nothing out of it. But yeah, I used it for. Yeah, this is the script generated by the. I've already showed it to us. Everybody hear this? Like, oh, really? But somewhat technical. Okay. So this is where I don't memorize the whole theorem and the proof. So that word. Sure can. You guys love it. Yeah, I was just like, oh, thank you. But it doesn't visit the same thing. That was too much. So based on
Like it's like the optimal place that all those steps are. Yeah, it makes sense. Well, it can last. I think. I don't know. My understanding is like you can go flat. Oh, yeah, you're probably right. You probably can't pass. You wait, there's like and then going back.
All right. Let's get started. Everybody hear me all right?
Yep.
Yes. Raise your hand if you can't hear me. How's everybody doing? I am not Burton again, but you may have recognized me from such lectures as a couple of weeks ago. Or if you have already forgotten, my name is David Healy. I am Burton's employee, in the sense that Burton is my boss.
He's amazing, right?
He's a great boss. Yeah, now that I know that this is being all kinds of recorded, posted on YouTube.
Did it give you feedback?
Unfortunately, no. My guess is that he did not watch it, but it could be that he watched it and he was like, "It's perfect. I don't have to say anything." So, could somebody give me a brief rundown of what you have talked about since in the last 2 weeks? The reason why I have some like background slides, but they were all stuff we talked about last time. So, what did we talk about in the intervening times? Anybody?
Last week was fall break. The week before that.
That's why. Okay. Week before that, was it just me? Am I the last person you've seen?
We talked about like image segmentation and like deep dream.
Oh.
When I think today we're supposed to talk about recurrent neural networks.
It's a good thing, because that's what I'm prepared to talk about. Okay. Recurrent neural networks. This is really honestly the best lecture that anybody could teach to people because it's so fun. Recurrent neural networks are the most fun that you will ever have had after you do them. So let's just jump right in. Okay, this is background. I'm assuming we're supposed to be covering this background. Okay, so convolutional nets. We have just sort of ended this segment on convolutional nets. But there's a lot of things that are overlapping between those and recurrent nets, which is what we're going to talk about today. In particular, in deep convolutional neural nets, what are the intermediate features looking for? That seems kind of like anyone want to give it a try? Hard question. Yes?
It's like the first shallow layer kind of identify edges more, and then it gets more abstract.
Right.
The deeper you go.
Thank you. The key word here is abstract, right? So at the beginning, they're looking for very granular features, and then hopefully, if it's happening right, what the deepness is doing is aggregating these granular features together into more abstract features, and even more abstract features, and even more abstract features, till hopefully at the end, you have something that can tell an eye, or something like that, and then something that can tell the texture that looks like fur, and that it's white, gray, and then the network can classify it as a cat. So we're going to continue along those lines. We talked about the revolution of depth, where increasingly performance on ImageNet, which is how we framed this, is driven by deeper and deeper networks. And the reason why those are good is because deeper and deeper networks can learn more and more hierarchies of features and more ways of combining features and more complicated things, so that at the end you can have something that can find an elephant. So there were a number of ways that we talked about to get depth. What was holding depth back at the beginning? Everybody remember? There's a couple of things. It used to be very, very, very hard to train a deep neural network. AlexNet was one of the very first, and it's only 8 layers. And then, oops, we talked about continuing on. In 2014, we started having really deep networks, 16, 19 layers, GoogleNet, which is 22 layers, I think. An important thing to point out, is that even these networks were very difficult to train at the beginning. VGGNet, they actually couldn't. You couldn't just train a VGG19. You had to start with like cutting off half the layers, 11 or so layers, and training the first 11 layers all by itself, and then like tagging on some layers after that. And the reason is that there are tens of millions of parameters, and they found that it was easier to train deep things if you can sort of get some of the parameters into a good space to begin with. So, yes, I keep going backwards instead of forwards, but I will learn. We talked about another way of achieving depth is by skip connections. We talked about residual networks, how they would take the input and add the input to the output of whatever the little block did. And this has the effect of when you're back propagating losses, so you're going to have a loss here, it allows these sort of shortcuts where you hit, the loss is going to come back here, and you're going to try to calculate the derivative of the loss with respect to whatever this is. And then that is going to get split, basically. And you're now going to calculate that loss with respect to both this and this. And that splitting allows the loss to sort of go through fewer passes and have less of a chance of vanishing the gradient. We all good? This all seeming familiar? Yes? Okay. All right, we talked about other ways of achieving depth. This is going to be somewhat related to what we're doing today, but not all that much. The dense net that we talked about had connections between every layer and every other layer. It's the same sort of idea as the ResNet, except now there's even shorter short connections. So the loss can propagate directly back to very early layers from the very end. And so you can get quite large losses at the early layers, and they don't have to be passed all the way back to the network. FractalNet did the same thing. The name of the game is getting the loss to have the option of propagating back through something very complicated so that it can learn through something very complicated, or also more simply learn from earlier stages. And that's sort of like a trend in going deep. So that's been driving deep learning. We talked about also that VGG and AlexNet in particular have tons and tons of parameters. But all of those parameters are coming from a single place. VGG19 has, does it say on here? I think VGG19 has like 140 million parameters or something like that. Just an enormous model. And that means that each of those, we're trying to learn a gradient of a loss, right? And the loss is just like a number. And the gradient of the loss is going to be spread across all 60, 100, 150 million weights. And so this is very difficult to do. But does anybody remember what the innovation was between VGG and things like ResNet and GoogleNet that allowed us to go save parameters so we could use the parameters for going deeper? Anybody remember what it was?
Just residual connections.
Residual connections helped. There's one thing that is even more. Residual connections help the gradient propagate backwards. The parameters, turned out, were all coming from the first fully connected layer, basically. The fully connected layer. So in AlexNet, for instance, the very, very last convolutional block was 256 by 6 by 6. and then you were learning a 4096 dimensional dense layer after that. And so that ended up being, you know, of the 62 million parameters, more than half of them were just in that one layer, which is crazy because that loss is going to hit that layer and then immediately be split into 40 million parts. And then you have another fully connected layer, which again, 4096 times another 4096, that's 17 million. And so the upshot was that all of these fully connected layers in AlexNet were like so much of the weights. All of the weights were just being learned in that last little chunk, and not necessarily in the convolutions, which is what we think of as being the main part of a convolutional neural network, the part that's responsible for extracting. So right, getting rid of fully connected layers and putting in instead. Anybody remember? So fully connected layers is because you need to flatten everything and get them into some, you know, you eventually need to just predict over like 1,000 different classes or something. And instead of fully connected layers, we ended up with, anybody remember? No, global average pooling. Global average pooling, where you just take these convolutional blocks and you just average them. And anyway, so because of global average pooling, which is another way of sort of summarizing all of the information at the end, we're able to have really, really deep networks, residual nets with hundreds of layers that are actually smaller models than the early ones. So, very cool. All right. Also, apparently talked about Instagram pre-training. This is the biggest pre-trained network on apparently 3.5 billion Instagram images, which would cost $29,000. It's actually not too bad. I mean, it sounds like a lot of money, but that's a huge model. And if you think something like your Facebook, and you're going to have your entire image platform built on this model that can correctly identify what's in it, $129,000 not too shabby. I think that was the opposite of the reason that was put up. It's supposed to seem like a lot of money, but okay. All right, now we're going to talk about recurrent neural networks. Okay, the idea of recurrent neural networks. I'm not sure I like this framing a lot. Your normal neural network, you put in an image or a batch of image, and what you want out is one thing. You want to know what the image is. So you have a classification, and this is one-to-one. Residual networks came about because people have other kinds of data that doesn't fit into this framework all that well. Again, there we go. All right, so for instance, you may have images, and you want to caption them. You want to like write a phrase, have a computer write a phrase out that describes what's in the image. So you still have one image, but now what you want out is a string of things. You want a string of words. And crucially, what you want is for each word to sort of depend on what the other words are. So this is what we might call like a one-to-many use case, where your input is one thing, but what you want out is many things. You may have a many-to-one scenario. This is sentiment classification. For instance, where you have, say you are a company, and people are tweeting about your company. And you want to know, you want a model that just like filters through all the tweets. You've made a deal with Twitter, and they're going to give you the tweets that deal with your company, and you just want a model that says, gives you out, you know, a sentiment number, 0 to 1. Is this positive or negative? So what you're getting in is a sequence. What you're getting out is a single thing number. You may also want something like that. Many to many. This is an extremely common use case. Sequence to sequence. This is how Google Translate works, for instance. You pass it in a sequence, a sentence, a bunch of words, and what you want out is another bunch of words. but also crucially, you don't necessarily want the same number of words out as you put in. Because if you're translating languages, for instance, you may not, the languages just may be different, and more verbose or less verbose, and you may not necessarily want the same number of sequences out as same number of steps in your sequence out as you put in. So that would be a many-to-many use case. Or you may, for instance, want exactly the number out that you put in. So this would be, for instance, video classification on the frame level. What is common with all of these except for the very last one? What kind of data is it dealing with? Anybody? Words. Yeah. To go off book just a bit, I would say that recurrent neural networks is usually about words. Like, for the most part, it was made for the use case of when you have words. And we'll talk about how they work, but the whole point is that when you have words, the words come in like a line, right, in the sequence. And each word, the context of each word depends on what comes after it, and to a certain extent, what comes before it. So these models, this sort of framework, recurrent neural networks, mostly used to do that. Now, that being said, there's tons of applications of recurrent neural networks. I'm using them right now as we speak for generating molecules that have nothing to do with words. But it's a good way to frame this in your head. That recurrent neural networks are made for dealing with words. Okay, here's the idea. You have an input. You're going to pass the input into, this is how we just show a node, right? But the node is basically has a matrix of weights that are going to weight each of the elements of X. And what you're going to have is then the recurrent node will do two things. It will both pass, it will have what's called a state, or sometimes they call it a hidden state. And for a single node, a single time point, that's usually just a number. It's a hidden state. And that state will be used both to maybe generate something at that time step. This is really confusing, and don't worry, we'll try to get into more specifics. But the idea is that its hidden state may generate an output for a time step, but it will also pass its hidden state to the next time step. You can think of it either as the next node, or the node corresponding to the next time step, or even it's sometimes drawn like this. You can think of it as passing it to itself, and it's going to take its own hidden state from previous as an input. Okay. This is a little more explicit. So a sequence of vectors, x, by applying a recurrence formula at every time step. So x at time t goes into the network, but also going into the network is h, which is the hidden state at time t minus 1. And then you learn some functions with parameters, and that's the new state. And then that new state is then passed on again. Hopefully this will become more clear sometime soon. Okay, yeah, very clear, very important point. You're not learning a different set of weights. You're going to use the same weight matrix every single time. In this way, it kind of resembles a convolutional neural network. You know, we get power out of convolutional neural networks because you can use the same set of weights and just slide it across the image. And then because of that weight sharing, it's like a regularizer. You don't have to learn like billions of parameters for every single pixel. You're just going to use the same weights over and over and over. And that allows, so this is a similar thing, but it's like over time. You use the same weights at each time step. Okay. So this is what we might call a vanilla recurrent neural network. As far as I know, nobody uses them, but this is good to understand the general idea. In fact, I think you won't get to recurrent networks that are actually people use commonly until the next lecture, but it's important to know what the sort of vanilla idea is. So you're going to have two sets of weights, right? One weight matrix that's going to weight the x, which is all of the features at time t. So if it's a word, you can think of this as like a word. X sub t is a word, and has a certain number of features, and those features may be the embedding of the word, or it may be like a one-hot vector. They're all zeros except for one of them. Anyway, so this x, you can think of this as a word, and you're going to learn a set of weights that will weight those features of x. And then you will also have a hidden state. So you're going to say, so this is like convolutions, right? When you set up a convolutional neural network, you say how many convolutional units you want in each hidden layer, right? That becomes the dimensionality of that layer. It's the same way in this case. So you're going to say, I want 128 recurrent units in this layer. So h of t minus 1 might be 128, a vector of length 128. This is all of the states at that time. So, t minus 1, so at the previous word. So I'm going through a sequence of words, and we'll get more specific later. But anyway, the point is, you're going to learn a different weight matrix for that as you learned for the x's, and then you're going to combine them somehow. And the way that recurrent neural networks are different from each other, or recurrent cells are different from each other, mostly have to do with how you calculate the new hidden state, how you combine things. And then it's, let's say we want an output, you can again learn a different combination of the hidden state to give you an output. So maybe your output is another word, or something like a word in a different language. That's not how we would do this, but think of it as a word of a different language. You're going to figure out how to take the hidden state, and the hidden state will specify, hopefully, what the word is supposed to be. Yes?
Yeah, so the ht is always dependent on ht minus 1, and then ht minus 1 is dependent on ht minus 2, and so on. Is there a way to tell the RNN that we don't want this dependency at a certain point of time? We don't want the dependency at all.
We don't want to what?
So since, okay, let's say we are processing words, and then we have a sentence, and then we know there's a new paragraph. So the two sentences have no relation between them at all.
Yeah.
In that case, this dependency is not valid, right? In the sense that the ht is no longer dependent on ht minus 1.
Oh, yeah.
So is there a way to solve that?
Yes, well, the upshot is that, okay, so there's two answers to the question. Yes, you can always force stuff like that by just saying, like, I'm never going to let the training set see anything that's not in the same paragraph. But hopefully, and this is not that hard, you get the neural network itself to learn that when there's a paragraph, this stuff is so cool, actually. I don't have a visualization, but you can find these visualizations. But you can get, the idea is to get the neural network to forget its hidden state when it receives a certain input. And again, that's a little more complicated. That will get into like LSTMs and GRUs and other more complicated recurrent cells that you will cover in later courses. But that's the answer to your question. So you try to teach the neural network when to forget its hidden state and when to disregard things from the past. Thank you for that question. Okay, this is the main point of the whole lecture, is to understand, to get a clear idea in your head of what the computational graph of a recurrent network looks like. Okay, so we'll say here is a weight matrix, or a cell with two weight matrices, maybe. We're going to say here's the hidden state of a node. We're going to initialize that, say, to 0. And this will say there is nothing, I've not seen anything yet, right? H sub 0. Then we will give it a word, say, and it will take the fact that it hasn't seen anything into account. It will weight that, and will weight the word, and then it will have now a new hidden state, h sub 1. Now we're going to say the next word, or the next character, or the next thing in the sequence. We're going to now pass that, again, to the exact same set of weight matrices. But this time with the new hidden state as an and then we'll get out a hidden state at time 2. Then we will say, okay, now here at time 3, and on and on and on and on. And the point is, at time t, this hidden state is now informed by all of the previous hidden states. So these are being passed along it in the same way that you pass along information in a sequential, like a forward connected neural network. Except now it's being sort of passed through time steps. Anyway, but it's the same basic idea. Yes?
For the thing, one of the diagrams, the arrow just show that it's kind of goes back into the RNN. So I wanted to ask, how is it depicted here?
Right, yes, good question. Okay, so in the last RNN we had a self-connection. Do we have markers? Yes, do we have markers? No. No, thanks. Don't let me steal it. I can get it. Steal somebody's. Thanks. Whose thing did I steal? Did you get it back? Big Bird said you got it back. Maybe he didn't come because he doesn't trust us. Okay, so so the two ways to draw this is called being rolled or unrolled. Let's make a list of terms that are very commonly used in this field. So you can say your neural network is unrolled. So this is what we consider like an unrolled version of the neural network. So instead of, so we'd say x, let's say x, big T, like the entire sequence of x, and that goes into hidden layer, current layer. And then you could say maybe there's an output at time t, I said t. And you can draw it like that. Or you can unroll it. This just means that every time step feed in the state of your previous time step. Or you can say, now I'm just going to break this up. This is going to be x1, x2, x3, x4, x5, and unroll the time, right? And you can actually make a neural network. You could probably just do this yourselves. Make a recurrent neural network the way you normally would, but through time, but unrolled through time. So. Okay, so anyway, those two things are equivalent. Did that answer your question?
It's like, I understand that like the computational graph, how it's on.
Oh, okay. Sorry, misunderstood.
When it's going back for the hidden layer to be used again, how is it depicted? Like, how does it go back into it and then it's used once again? Is it used in the old states or for a new state?
How is it depicted?
Yeah. As in, can I?
Sure.
So my question is, when it's going back, how is it depicted? We realize that from the graph, the H0 is used by the function then to give the output. So how does it?
Okay, so in this case, the H0, H1, H2, and H3, all the way up to HT, are the same thing. And they're the same node, the same recurrent cell. And those are not the outputs of the recurrent cell. It's just, those are just showing the hidden states of the recurrent cell. So I actually think that there's an example that's coming later that I think will make it more clear.
So this is still our echo.
Right, yeah.
The
And putting this, drawing it like this just means do this. It just means pass the hidden state of in back to itself at the next time. Okay.
Do you add like the hidden state and the input? Do you just add them together? Is that what you do to combine them?
Well, you do complicated things with them, but in this case, what we have is you weight both of them separately, and you add them together, then you apply them.
Okay.
That's like a simple thing.
Typical.
That's probably not the most typical way that these are usually done, but this is like the most vanilla way to describe it. So a lot of times they can get pretty complicated about ways that the things that are inputting and how to combine them. But you should just think of it as, it usually ends up something like this. You're going to have a great time with Berg in the next lecture when we talk about LSTMs. Okay, so again, we're using the same weight matrix. What that means is it starts to look a lot like those dense nets or something, where there's a lot of ways for the loss to get back to that weight matrix. It can get back through any of the time steps, and then combinations of all the time steps as well. Okay, so for instance, if you have a many-to-many scenario, you may want at time 1, right, x1, and you want a y1 as well. So let's just imagine that we are translating a language, and we want the exact same number for some reason of words in out as we get in. So we say for each x we want one y, or each x1 we want a y1, which is just this word translated into a new language. Obviously it's more complicated than that, but just so you anyway. So this output will be a function of the hidden state at time 1 after it's received the input. The second output will be the hidden state at time 2 after it has received both information from hidden state 1 and x2, etc., etc., etc. And you can calculate a loss on each of those, or you can also maybe calculate a loss on the entire sequence in the case of translation, for instance. So you may have a loss on the whole sequence that says, how well did I do at translating the sentence? Oh, you did terrible. And then that loss gets propagated back through every single time step, potentially, back to the same weight matrix. Yes?
Is there a function that's going from h1 to y1?
Yes, yes. So
that's not shown.
In the simple case, so the answer is, whoops, I think I'm going backwards, but instead I'm going forwards. So in the case that we showed here, it was just, there it is. In the case we showed here, it's just a weighting, just a linear combination of the, yes.
Is it the same weights for every single h at each time step?
Yeah.
So then, when this, like, I guess I'm confused. I see how the loss gets propagated at each out, but you're not doing back propagation at each time step, are you?
So yeah, the answer is yes, you are. Yeah, you are. So this is the sort of like unrolled version for ease of looking at it. But oh, I see. No. So your question is, are you back propagating each time step?
Are you back propagating each time step? Because I don't get how there's an arrow drawn from the function at each time step. But it's, oh wait, no, I'm determining the drop. That's the weights. Never mind.
Okay. We're going to do a really nice example of how this works that should help figure this out. Okay. You may also want a many-to-one. I don't know why they put the more simple thing later, but you might say, okay, all right. So the many-to-one, let's say you're classifying sentiment. All you want is the sentiment. Typically, the way that this goes is that you will read the entire sequence in, pass it along, da 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 da, and then you would predict something only off of the last time step. And hopefully, this hidden state, set of hidden states anyway, hopefully represents the sentiment of the tweet, or this, whatever it is that you're trying to predict. So you usually make this off of just that thing. So this is a way of embedding an entire sequence of things. Yes?
Does the hidden state get reset to the same values every time at test?
At test? No. We'll show what happens with test. Okay. So what is it? This is the same. Okay. This is a very important use case. Really, how? This is not. Okay. You can think of this as a good way to do translation, right? If I have an English sentence and I want to turn it into a French sentence, but I don't know how many steps it's going to take, I don't want to constrain it to a certain number of steps. So what I can try to do is represent the entire sequence x1, x2, x3, which is the English sentence, as a single vector, which might be the hidden states of what we would call now the encoder. Because this has encoded now this entire sequence into a single vector that now lives in vector space, which is an interesting thing to think about. It's a sequence that is being represented by a single vector in vector space. So, like, you could imagine yourself walking around that vector space, and each point in that vector space represents a different sentence or something. Okay, so we now can then take that, and we can use that as the initial state of another recurrent neural network that's one-to-many. So we did a many-to-one, now we do a one-to-many. And so this is like the example of, what was our example of one-to-many that we did? It was like image captioning, right? Where you pass it a single image, but what you want out is a whole sequence. Now we have a decoder that says, this is the English sentence, H sub t. Here's a vector that represents the English sentence. The decoder now has to learn how to turn that vector back into a sequence. And that sequence can have any number of time steps, or a different number of time steps that the input sequence has. So this is a very common way to do, this is called seek to seek. It's a very common way to do translation and things like that. So, okay, so does everybody see how this could be like an encoder and a decoder? Yeah.
If the H of t represents like English sentences, then what does the x1 and x2 represent?
Yeah, so the x1 and x2 are individual, you can think of them as like individual words in a sentence. And the h sub t is a vector that represents the whole sentence. It's like an abstract representation of the entire sentence. So it's now no longer like the elements of the vector don't have anything to do with the order of the words. It's now just a single, this vector is 2, -1. That means, that represents this English sentence or this concept or something like that. Yes?
Maybe I don't understand the decoder all the way, but let's say I have a sentence of 10 words, and I want to translate it to French. Right? And how do I know how long the French phrase should be?
Yeah, this is why this is so magical. Is this hidden state here? It actually kind of similar to the way that you would really translate from language to language, is that you would hear something and try to get a complete idea of what the thing is. And then you would take that idea and say it in the other language, instead of trying to translate like each word. And so that's the idea of this kind of model. Okay, let me just check on the time here. All right, I think we're good. Okay, so this is our example. This is where you should actually start understanding. Okay, so language model. This is another important term. Language model. A language model just says what is the probability of a sequence of words, sure. Which is like, what is the probability of some word at time t given all of the words before? Okay, this is what we mean by language model. A character model, character level language model, or a character model is just like a more simplified version of this. We can just think of saying we have in the English language 26 letters. Maybe we need some punctuation, so we'll have like, 60 different characters or something like that. And what we want to learn is probability distributions over sequences of those things. This will make more sense. Okay. The reason why we do this a lot is to generate language, so we'll talk about that as well. All right, so let's imagine that we have only 3 characters in our vocabulary, H, E, L, and O, and we want the model to learn that hello is a word. So we're going to describe the process of training this. So we may have a sequence hello, right? And the task for the model will be, at each time step, or at each point of this sequence, we're going to tell you what the letter is at that time step, and you have to predict what the next letter is. So that's the task for the model. So at time 1, so we may at time 1, for instance, so we're just going to represent these as one-hot encoded vectors. That's common. You can also try to embed them somehow first. But we're just going to say if it's a 1 in the first place, it's an H. If it's a 1 in the second place, it's an E. L will be in the third place, and O will be in the last place. So this is how we're going to, our input will look like these concatenated. So in the first time step, we have an H. Whoops, there we go. All right. Now we're going to feed it into a single node with a hidden representation that is of dimensionality 3. So forget about all this, just look at this part. So at time 1, it's getting an H, and it's got some hidden representation that is a function of this vector, right? We've weighted it somehow, and it's produced this. And it's also getting in, though we haven't shown it, the previous hidden state, which is 0. So it knows that H, it knows that it's an H, and it knows that it's the start of the sentence, the start of the word. So it's going to come up with some representation for this scenario, and that's the hidden layer state. Is everybody good? Yes? Yeah.
Is this the whole process trying to simulate the word completely?
Yes. Yeah. So that is one way. That is one way that we do that. So language models are what drives the word completion. Okay. So right. So now it has this hidden state, and this hidden state just represents the state. The state is that it's an H, and the H is the beginning of the word. Now we say next time step is E. So we'll pass this in, again, the same weight matrix, W sub XH, has to weight this E, but it also gets the fact that it was an H before and it was the beginning of the sentence. That fact gets passed to it as well. So now it's just like taking this state and it's updating it with more information about the next one and the next letter, right? And then we do that again and again. And at each time step, this hidden representation is supposed to represent the state that we're at. Meaning, over here, it means we have seen H-E-L-L, right? That's what this -397, -0.3, 0.9, and 0.7 should represent, the state that we have just seen these 4 things in a row. And then, what we'll say is we want you now to predict at each time point what the next time step is. So again, going back, time step 1, we pass in the H. We get a representation of the fact that it's an H and it's the beginning of the word. Giving only given that information, the model has to predict what the next letter is, right? So its output layer will be 4-dimensional because there are 4 characters in our scenario, H, E, L, and O. Marked here is green is the correct answer, but you can see maybe that, for instance, the model thinks that it's an O, because 4.1 is the highest. So it's going to like softmax this, maybe, and come out and say it's an O, but no, it's not an O, it's an E. So that's a penalty, you got it wrong, that gets passed back to this weight matrix here. And the previous state weight, this weight matrix here as well. Okay, so next time step, we say, okay, we now have HE. Here's the new representation. Here's our prediction of what happens when we have HE. We think that it's an O again, but it's not. Got it wrong. Pass the loss back. Okay, now L. Update the weights, or update the hidden representation. This hidden representation now says we have HEL. What's our next guess? Oh, look, L. We got it right. The loss will not be bad. And then on and on. So this hopefully is giving you a better idea of how these things are trained in real life in this example. Yes?
2 questions. Sorry. When the loss gets passed back, like let's say we're on time 2.
Yes.
Does the loss get passed back to time step 2 and a time step 1 somehow?
So because this WXH and this WHH are the same weight matrix at each time step, when we pass it back at time step 2, there will be a loss here that will get split between applying to WHH and WXH. Also WHY, right? We'll also penalize it for saying, oh, you guessed the wrong thing based on the hidden state.
And each one of those has already been updated for the first time, so that's how that's taken.
Right, yeah, so that has been updated and updated again and updated again. So the way this actually happened, this is what, even though it kind of looks like a many-to-many scenario, this is a many-to-one scenario. Because we may have, we may have, the goal of the model is to predict the next letter based on all of the previous letters. Yes?
What's the relationship between the number of entries in the hidden layer and the input layer?
Say that again?
What's the relationship between the number of entries in the hidden layer and in the input layer?
The relationship between the number of entries
Entries in the hidden layer and the input layer.
Oh, right. So, yeah, the hidden layer is an arbitrary number. So we'll just say, like, when you're in TensorFlow or whatever calling this, you'll say, I want an RNN of dimensionality 3. And then those, and it's like any other neural network layer where the weight matrix, this WXH, is a 4x3 matrix, right? It's weighting each of these and outputting three new numbers. Does that make sense? Okay, so this can be arbitrarily big or small. We could have done this with 1 number in the hidden layer with 10 numbers in the hidden layer, however you want it. It just depends on how high dimensional you want the representation of the state to be.
So when will we go for high dimensional representation of data?
Yeah, you want more high dimension. It's like convolutional neural networks in the sense that the more complicated of dependencies you want to learn, the more capacity you want to give the model, the more dimensions you want to give the hidden states.
So is this similar to the high level of abstractness that we want to introduce to the network?
Kind of. In convolutional networks, we typically think of abstractness being the depth of the network, sort of like how many different nonlinearities there are in a row. This is more like the width of the network. So this is like, if you say, I'm doing a convolutional layer and I want it to be 128 nodes. That 128 is the dimensionality of the convolutional layer. Same thing here, yes?
For the nonlinearity between the hidden layers, the slides have been writing hyperbolic tangent.
Yes.
Why no ReLU?
Good question. That will be, I think, covered in later classes. But it is a good question. Yeah.
Is it also like a hyperbolic tangent going from the hidden layer to the output layer, or is it a different kind of function?
So in the example that we it's like this thing points forward, but it actually means backwards. In the example that we gave way back here, the output was just a linear combination of things. But typically you would have some nonlinearity there. But you can do whatever you want. Okay, so here's the main point. These sort of language models or character models have two kind of modes. This was training. This is how we trained it. But you can also just call it test time or prediction time, where you let it generate. You give it nothing and let it generate. So here's how we do that. We say, okay, here's our vocabulary. We've trained our network. Hopefully it understands things now. And we're going to say, here's an H. That's all we're going to give it. Here's an H. That's what you got to start with. Okay, so it'll say, all right, I've learned from the training layer what to do with an H at the beginning of the sentence, right? I know how to represent it. I know it's going to be an E. So it'll say, it's an E. You say, oh, good job. Now you say, you take what it outputted and put that in as the next input. You say, okay, now we have HE. Propagate it, forward. Now, and the network says, I think it's an L, right? H-E-L. That's not exactly what this said. This network thinks it's an L. I don't understand. Okay. Anyway, so it may guess it right, it may guess it wrong. Actually, I will say something about that in a minute. But whatever it guesses, okay. Oh no, I understand why this is the way it is. Okay, so typically what will happen is you will have some sort of sampling function at the end of this. You don't necessarily want to make an argmax in a language model because you'll just get the same sequence over and over. But you might, so there's typically a temperature parameter with these things that says, when you're generating, that says, like, how soft should this softmax be? And then it'll sample from that softmax. So let's say this is the output, it knows it should be an O, but instead, for some reason, it sampled an L, an unprobable event, but it did anyway. Well, that was lucky, right? So then we put in the L, propagate it forward, says it's an L again, samples another L. It does that anyway. The point is that you're taking the output at each time step and feeding it in for the next time step. Now, there's a thing called teacher forcing. Which is what we did before, where when you're training it, you force it, you basically, no matter what it samples at the output, you put the correct answer in the input. And this is to make the model learn things that are real, that are really going to happen in real life. Anyway, okay, so this is now a generative process, right? We can just run this indefinitely, and just run the model, and just say generate language. And this is, anyway. So this is the use of language models and character models, and they are so cool. Okay, one point about back propagation through time. Let's imagine this is a giant sequence. Let's imagine it's like an entire article of Wikipedia, which people sometimes have as training samples. This loss is, you could try to propagate it at every single time step, but in practice, sometimes what people do is run it forward and backward through chunks of the sequence instead of the whole thing. But so you'll say, okay, take the first 10 words, we'll train it through the first 10 words, and then we'll just pass those hidden states on, train it with the next 10 words. And this is kind of like batching, but through time. And you're carrying the hidden states for each time. Okay, that's just a note. All right, so these things sound complicated. But if you go and find Andre Carpathy's GitHub repo, there is a miniature character RNN that does what we have just described, but with all the characters. And it is 112 lines of Python in NumPy. This is not with dependencies, just NumPy. Anyway, highly recommend you take a look at this and just see what's going on to help you understand. All right, here's a thing you can do. You can take, for instance, all of the entire works of William Shakespeare. Just say only the sonnets. And you can feed those in as a training sequence with this character model. So each character separately, just like the AGLL we were doing. Do that with all of the characters of English and the entire works of William Shakespeare. And this may be some sonnets. We're going to feed them in. And then after a couple of time steps, we'll say, okay, let's pause the model, generate something. This is what you generate at first. Gobbledygook, right? Train it some more. Starts looking like, there's an actual word right there. Also, it's starting to get like the length of words kind of right. So it's like learning where to put spaces, and it's even realized that it should capitalize things sometimes after periods. Train it a little more. Now it's kind of looking like it's actually getting, Arwich-5ing word to it. It's actually getting real English words. Train it even more, and it starts to actually make sense. Well, not make sense, but it'll actually be words, yes.
I didn't get how it will generate on its own without the input.
So this is, again, this is this scenario here, where we typically seed it with something. You say, I want the first letter to be this, or you'll say, I'm going to seed it with blanks. Or you could say, I'm going to seed it with a sequence. You can say, I want to seed it with From Fairest Creatures We, or something like that. So that becomes the first input. And then, again, you are taking the output at each time step and feeding it in as the next input. And so this thing just goes on and on and on and on forever. Yes?
So in like the example that you chose, this one, are you passing in the space character as
Yes.
like A through Z?
Right. So the space character, or paragraph break, or capitalization mark, those will typically be separate characters. And so what you get if you do it for a long time, and anybody can do this, just a single GPU probably, and it'll take you, a few hours or something with an LSTM, you actually get, and this is genuinely generated by a recurrent neural network, a character model, you can get it to learn really interesting things. And these are all just based on what is the probability of the next character given the last character. So it learns, for instance, that it's a play. So you fed it all the plays. So it learns that it needs to capitalize a bunch of things and then have a colon and then have a bunch of non-capitalized things. But the things, it's actually learned, like, attained its being never fed, and who but a chain and subjects of his death I should not sleep. I mean, these are things that are just, that is all it is. These are all generated just by that character model that we just showed how to train. Right? Pretty cool stuff. This is why recurrent neural networks are the funnest thing, is because you can just get them to generate. I once generated a bot of my professor friend who's a professor of philosophy. He's a professor of moral philosophy. I took all of his previous writings and I fed it into a character neural network. And now it just like rattles on about people and their rights all day long.
Why do you use characters instead of words?
So you can use words. This is easier to train.
Oh, okay.
Definitely people use words as well. But with words you need a vector of like 20,000, to represent each word. So just for the sake of understanding. But even here, you can see how it even just on a character level, it's learned these long-term dependencies in the sequence. That it has to capitalize everything after it has to have a comma at the end to capitalize the next line. It learns all this stuff. Okay, they did this with LaTeX, a giant LaTeX online topology textbook, and this is what you get out. It's figured out how to make equations. Equations don't mean anything, but it's figured out that you need proof, and it has lemmas, and it numbers the lemmas, and numbers them in order even, which is crazy. Isn't this crazy? For this 3 to be here, it has to know that this 2 was here, hundreds of characters before it. For this 2, has to know that this point 1 was here. Anyway, but it's very long-term dependency.
Is it learning the tech commands, or is it just learning the text?
It's just learning, all it's learning is the probability distribution of what character comes next, right? So they trained it on the raw LaTeX.
Oh, on the
Yeah.
tech code, okay.
And then they generate it. So, cool. It knows how to close parentheses, but not all parentheses. There's just got to close one, but no open. So it does make mistakes, right? But it gets the general form right. Yeah.
So here the author learns the grammar of Latin.
The what?
The grammar.
Yeah, the grammar. Yeah. Yeah. And it learns English, and it learns math, and it learns, how LaTeX is compiled and what the things. It learns even to draw diagrams. But it knows how to draw diagrams just by learning the code. The other cool thing is that it will omit proofs. I'm not gonna do that. Yeah. Anyway, it knows that you need a couple of lines of text, and then you need to do an equation, right? So they've also done this with Linux, and it generates, the Linux kernel. It generates C code, right? It knows how to indent. It knows how to close out, how to balance parentheses. It declares variables. It doesn't necessarily use them, but it declares them. And this doesn't compile, obviously, but it looks like C, right? Anyway, these character models are incredibly powerful because of the kinds of things they can learn. Oh yeah, here's the beginning. It learns it's like a new public license. It knows that it has to have it, and then it has to have a bunch of includes, so it just knows, because, that first hidden state, right? You pass it a hidden state that just says, we're at the beginning. It knows exactly what to do. Just start with the public license. Anyway, it's pretty amazing. This is going to be, okay, we're going to see if you can hear this. This is a script that was generated with a character model. It's where they fed it. Well, I think the video will actually say what it is. They actually produced it, right? Thomas Middleditch did it. People hear this? So these are the screenplays that it learned from. Terminator, X-Files, X-Men. So the random seeds, that's the beginning, right? That's what you see it with. You say start with this. Start with the title, some dialogue, and then just let it run, right?
In a future with mass unemployment, young people are forced to sell what?
You should see the boy and shut up. I was the one who was going to be 100 years old.
I saw him again. The way you were sent to me. That was a big, honest idea. I am not a bright light.
Well, I have to go to the skull. I don't know.
What do you mean?
Well, I don't know anything about any of this.
that these are directions that I wrote.
There's no answer.
We're going to see the money.
All right, you can't tell me that.
Yeah, I'm coming to that thing. Who's your sir? Really?
I don't know. I don't know what you're talking about.
That's right.
What are you doing?
I don't want to be honest with you.
You're a doctor.
I'm not sure. I don't know what you're talking about.
I want to see you too.
What do you mean?
I'm sure he wouldn't even touch me.
I don't know what you're talking about.
This wall is completely constructed at the same time.
It's all about you to be true.
You need to touch the movie with the rest of the base. I don't care.
I know. It's a consequence. Whatever you need to know about the presence of the story, I'm a little bit of a boy on the floor.
I don't know. I need you to explain to me what you say.
What do you mean?
That
That was all the time.
This is the lyrics of the song.
Beautiful day out in the storm.
I just wanted to tell you that I was much better than he did. I found him. I couldn't even tell.
All right, I'm gonna stop there. So there's an opportunity here to sort of like think about what's really going on, right? This is a character model. You saw the script that it made, right? The script looks like a script. It's got people talking. It even has sort of like the right length of things that they're saying. But does it make any sense? No. Well, somewhat. Yeah, I mean, I think the actors take a lot of liberty, with their acting to try to make it seem like it's making sense. But it's just all it's doing is learning a probability distribution over what the next character is, given the previous characters. That's the entirety of what it's doing. And so it doesn't actually know anything, really. And there's no continuity, right? It doesn't seem like it's making a plot. It's just all of, this is what you get. This is what you get from recurrent neural networks, character models, language models. Now, hopefully, when you talk about attention and some other other sort of techniques in sequential modeling, you can start to get better at this, learning very, very long-term dependency. This is the difference between this model and say, if you let like a second grader write a script. The script might be about something. There might be like a theme. There might be like the second grader may remember what it wrote at the beginning. But all of these things sort of have, even if they seem to have kind of like a long memory, it actually tapers off pretty quick, right? You get sentences that sound like sentences, but you really don't get paragraphs that like have a continuity. It's all always happening. Okay, are there questions? But yes.
So the problem here isn't, it's partly because of long-term dependency, but it's also because of, just because we fix long-term dependency doesn't mean that all the context problem will be solved, because there are certain domain knowledge that we know that makes sense, but it's not entirely going to be solved by long-term dependency.
Yeah, no, it's not just a long-term dependency problem. That's right. There are, like, Google, for instance, has gotten language models to generate Wikipedia articles that will, like, seem to have a little more continuity, maybe. So it's hard to say how, when we think of ourselves generating something, we certainly don't think of it in terms of a long-term probability, a long-term dependency of a probability distribution, right? we think of ourselves as having like a concept in our head of what we want to write about. That's definitely not how these are working. But they, they sort of imitate the form of language. Okay, are there any other questions about recurrent neural networks?
Does it also predict where to stop?
Yeah, typically. So you'll put, if you have a, anyway, yes is the answer. So like, if you have a sonnet or something, you'll have a line break character. That's one of the characters that's line, but you also have like an end of sonnet character. So but each of these are represented by a sonnet. Any other questions? Okay, all right, we're done. Have fun. Play with these. These are great. Make a bot of yourself. Look at all of the emails that you've sent in your entire life and see if it can sound like you. So
the new keyboard update is kind of scary. It's like stuff like that. Whenever you have everything in the subject, it's like trying to predict what's coming out. Like as you're typing the subject, like tells you like it can judge if you want to say like regards to like things or something like that based on the subject. I don't know.
If it was personalized, that would be a little creepy. So I know, like if it was like filling in your mom's, whoa, I don't know.
I did like the subject saying internship, and then it tried to guess like applications, like at the right actual bodies. So I was kind of scared out of that. Like, man.
Yeah, you learn really cool stuff that's like beyond just recurrence. Other ways to make models really good.
Thank you.
Yes.
I'm curious, kind of in like a bigger picture discussion. So I'm super interested in the subject, and I'm kind of like deciding if I want to do this medium and long term. Like, what does a day look like in this study, right? Oh, you work here, so for your weekly, right? You do.
Yeah. I'll tell you what I do. I'm not sure how. I come in, I open up my chart. So today I spent there. I'm trying to show for publication. Again, like most data scientists publish publicly, so that'd be typical. But for publication, I show that there's two different kinds of inputs. You can just do that. And those inputs take so anyway, I've been making a framework so that I can easily train these things with different combinations. That's what I did. So today I was debugging that framework versus
that do
different models.
Are you can communicate like red and that's it. I can believe that you I don't know.
So I would say that depending on where you go, it is still pretty varied. So so you can kind of be a machine learning engineer, probably most computations probably do analysis, which is data. The next one's probably building
deep learning or
like wrappers around.
Machine learning is not
Deep learning sort of software machine learning that will take in some data and score them, pull it back, and score things.
Because like machine learning has also like
And then there's what I call science. Here's a use case nobody knows.
clustering and like all that stuff. That stuff is this machine learning, but it's not. And there are like, for example,
Well, I got it.
like a lot of Bayesian models, they are not ROS is straight. These are like segmentation, other things. These are these kind of things like you can understand like the general way.
So, what's the education look like in this genre?
But
Yeah, it depends. And it's like a thing that is always has changed a lot. When I started, which was 3 years ago, at a PhD, and it seemed like a lot of people that I met were PhDs and science PhDs and stuff.
it's really tough.
And they hadn't been formally trained in data science. So a lot of people like me, if you look at PhDs and stuff,
Data image that can be n-dimensional image, the ultimate.
so yeah, I think that that's what you're asking about, graduate degrees and stuff.
Yeah, just to give you some context, right? I'm an undergraduate, and at the end of the semester, I will have finished every grad course that you offer.